We're all familiar with gas. What makes balloons go up, the air we breathe, the fuel that helps us cook food, and dry clothes. But gas is actually a state of matter and totally dependent upon external forces to keep it that way.
Whether or not something can be in a gaseous state depends entirely on the conditions that it's under, its temperature and its pressure.
At the centers of distant massive stars, iron exists as a gas. While on Neptune's largest moon, Triton, nitrogen, which makes up over 70% of the air we breathe, is frozen solid. In our own small corner of the universe, the relatively stable pressure and temperature here on Earth allows 11 elements to occur naturally in gaseous form. But there are many more gases out there. Some are composed of different combinations of elements that form molecules, while other substances can be turned into a gas, such as water into steam, by adding heat or reducing pressure.
Gas has neither definite size nor definite shape. So if I take a gas and expand it into a confined shape, like a bottle or a glass, it will easily expand to fill that bottle, and it will take on the shape of that bottle.
That's because gas is composed of numerous molecules moving chaotically in all directions. And from that chaos comes, among other things,
This is because natural gas is made up of compounds that have carbon-hydrogen bonds. And in the presence of a high fraction of oxygen gas and at elevated temperature, those carbon-hydrogen bonds will react with oxygen to make carbon-oxygen bonds and hydrogen-oxygen bonds.
Simply put, natural gas is a great source of power because it burns, and very cleanly, producing 50% less carbon dioxide than coal and 25% less than oil. Composed mostly of methane, it develops in underground geologic formations from decomposing plant and animal matter. In the U.S. alone, the Department of Energy estimates that nearly 975 trillion cubic feet is trapped in subterranean reservoirs, and the only way to get to it is by drilling.
We're now on the drilling rig floor. This is the real first step in the operational phase of being able to drill for and develop and produce natural gas. As you can see from the drill pipe located here, we're actually applying the rotational energy through a top drive system, which is more of a modern technology that we have. This allows us to drill more efficiently and more quickly. By utilizing a top drive system, we can vary the speed at which we want to rotate the pipe and actually hoist the pipe up and down in a more efficient fashion. This particular well is a horizontal well. The way that we're able to do that is we actually drill down to a certain predetermined kickoff point and put some tools into the ground which allow us to build an arc and actually go out into the horizontal plane. In a case like this, we'll actually drill a lateral out anywhere from 2,500 to 3,500 feet from this surface location. In some cases, we'll actually drill at higher than 90 degrees. We'll drill up a little bit. That will allow us over time, as we produce fluids into that lateral section, will allow those to gravity feed into the sump of the wellbore, more effectively get those out of the well, and ultimately increase the productivity of the gas.
What comes out of the ground is usually impure and must be processed before it can be used.
As far as the gas coming from the wells, we have thousands of miles of gas pipelines, anywhere from 2 inches on up to 24 inches, that gather the gas and bring it to the central facility. I kind of describe it like the spokes of a wheel, and the plant sitting in the middle of that wheel.
The first step for producers is to remove the groundwater in the gas. By putting the product in simple storage tanks, they allow the gas to rise while the heavier liquid sinks to the bottom. Raw natural gas is actually a combination of fossil fuels. The next step for producers involves separating and purifying each of the gases. Many complicated methods of separation, from pressure and temperature manipulation to chemical, are used, depending on the gas's composition. Here at the Devon Energy Bridgeport plant, outside of Fort Worth, Texas, the preferred method is cryogenic cooling. Inside of this 140-foot tall spire called the demethanizer tower, the gas is about to become a liquid.
Okay, in the demethanizer tower, we basically have the gas stream flowing up through it. At the right temperature, those molecules start gathering together and forming droplets. At a minus 170 degrees, just like rain, they start falling to the bottom of that vessel.
The liquids that form, such as propane and butane, moved to these tanks for storage.
They represent a very small portion of our business, approximately 15%. The remaining 1.6 million gallons that we produce are sold down pipeline to the nation where they are distributed. The other 530 million cubic feet per day that we bring in as natural gas is sold as methane to the residential and industrial users throughout the area.
But getting the gas out of the ground and into a tank is only a small part of the story. Today, natural gas supplies the United States with over 20% of its energy. 1.1 million miles of pipeline crisscross the country, making the use of natural gas as easy as turning the knob on your stove. The exploration, drilling, and processing of this fossil fuel into a clean-burning source of power has helped mold the modern world. Petroleum companies could easily load their liquid products onto trains or trucks, but that didn't work for invisible, odorless gas.
It wasn't until pipeline welding was perfected about the time of World War I that gas could be transferred significant distances. Then, of course, the economic downturns during the Depression and World War II meant that there was not significant demand for natural gas. And it was only after World War II where both the need and the technology to transport gas coincided that we have a significant increase in natural gas use.
The timing was perfect. The consumer world was about to take a giant step into the future, and natural gas would provide both the power and the product.
And it was opportunities such as plastics that developed in the 50s that really stimulated gas use. Natural gas is both the fuel to run plastics factories and is the raw material that is used to make the plastic that was so significant in our lifestyle changes since the 50s.
Between plastic and pipelines, natural gas was no longer an alternative fuel. It was becoming as big a part of consumers' lives as gasoline and electricity, and its use would continue to grow. Today, that growth has led to a wide range of natural gas delivery systems. This strange-looking tanker ship is transporting over 125,000 cubic meters of natural gas, which will be unloaded at a specialized terminal. But most of the natural gas we use arrives via a complicated array of pipelines and distribution centers that push the product to consumers around the country.
So on an annual basis, we move about 1 trillion cubic feet of gas, which is a little less than 5% of the total gas consumed in the United States.
The natural gas enters the system from the producer's 30-inch diameter interstate pipeline. Though under pressure, the natural gas moves slowly. For distributors, forecasting how much gas their customers will use is an important part of the job. This is one of the largest natural gas storage facilities in the western United States. What makes this site, conspicuously absent of tanks and steel pipes, so valuable is the geologic rock formation over 10,000 feet below the surface.
The reason the storage reservoir is here is because 2 miles beneath my feet is this kind of rock. This is a porous sandstone. 20% of this rock is pore space, just like the space between the grains of sand on the beach. And that's where we compress the gas and place it in that porosity. We can fit 50 cubic foot of gas into every cubic foot of the rock. This is an impermeable shale. 200 foot of this shale sits on top of this sandstone, and that's what seals the gas in place, so it's there for us to deliver when we need it.
For natural gas distributors, getting the gas back into the ground takes almost as much work as getting it out in the first place.
Behind me is the main compressor building. We've got 5,500 horsepower units in the building. Right now, 3 of them are operating, and they're injecting 125 million cubic feet of gas per day. This gas is being picked up off the pipeline at about 600 pounds per square inch pressure and being injected into the ground at over 3,900 pounds per square inch of pressure.
To put things in perspective, our storage capacity is large. It's enough gas to serve the 20 million consumers in Southern California for about 3 months.
When the natural gas is needed, it's pulled from the ground and gets a good cleaning. Separation tanks and cooling towers, similar to those used in the initial refining process, remove dirt, water, and heavier hydrocarbons that have contaminated the gas while underground. Once back in the pipeline, the product is odorized and continues its journey to the customer.
Once we get near the homes, we run individual lines to each home. Those are very small diameter lines, usually in about a ½ inch diameter. When the gas gets to your home, it actually is about 1/3 of a pound pressure because we have a pressure regulator at the house adjacent to the meter that you see at your home. This is the device that our meter reader looks at when they come around monthly.
Surprisingly, most of the natural gas we use never comes directly to our homes.
We bring in about 3 billion cubic feet on a daily basis. About 1 billion of that goes to residential and small commercial customers. The other 2 billion go to the large customers.
And those large customers use natural gas in power plants to produce electricity and in all forms of manufacturing. Manufacturing that helps make up the world in which we live. In the end, the product that captivated early humans as it leaked from the ground now powers our world.